We're ready. Okay, let's just get back on the horse. What were we doing yesterday? Yeah, we were differentiating trigonometric functions, and I said to get to this very simple result, the derivative of sine is cos. The derivative of cos is minus sine. I was thinking tan and saying sine at the same time. And the derivative of tan is, do you remember? Sec squared. Anyway, to get to these results, requires all of this stuff. Okay, so here's what we did. We said we would go through the textbook approach backwards. Okay, so we just looked at the graphs and we thought, what does the gradient look like? And we got a general sense of it. Okay, then we looked at first principles and we used trig expansions and we broke apart limits and all that kind of thing, and it worked out. But, and this is where we got up to yesterday, right? I gave you this limit as h approaches 0. I said that this limit was equal to 1. Do you remember that? And I sort of looked at the graphs and I was like, look, it's kind of close, but we don't really know why. Okay, so you can see that's why textbooks do it in this order, so they get a result and then that allows you to prove the next bit and so on. Okay, but I think it's less intuitive. So now we've used this result, can we show why it's the case? Okay, so right now I'm sort of doing 2 and 3 are sort of together. Okay, so let's do this at the same time. You might want to make a heading which is squeeze law. Okay, so we're picking up, we've done 4 and 5. Okay, well, actually we did 5 and then 4. So now 2 and 3, they sort of do clump together. So we're going to do them both right now. So, to start off with, before I explain what the squeeze law is, I want to give to you a scenario, which is that this is similar to what we did yesterday, right? If you draw 3 graphs on top of each other, and I'd like you to actually draw these just roughly. If you draw sine, then you draw x, the straight line, okay, like so, and then you draw tan, which has an asymptote there. Okay, so I've just drawn a very, very small part of tan. Okay, the section of this graph that I'm interested in is the domain from 0, the axis, to pi on 2. So that's just that little bit in here. Okay, 0 to pi on 2. Okay, so where x is acute, basically, right? Can you see, how would you describe the growth of each one? Just in this little section here. So in fact, I'm going to forget about the rest of the graphs and the parts that we're looking at. Okay, so this is actually the part that I would like you to have drawn. Okay, let's describe these 3 graphs and how they are behaving. Each of the graphs, right, their gradient is positive. You see that? They're all increasing. But they're not all increasing at the same rate. Okay, so for instance, sine. Sine is increasing, but it's increasing at a decreasing rate. Does that make sense? Yeah. Increasing at a decreasing rate. It's still going up. That's what increasing means. But it's sort of slowing down. It's like you're running up a hill and you're like, getting tired, right? So that's what I mean by increasing. You're still going forward, you're going up, but at a slower and slower rate. Until, in fact, when you get to pi on 2, you've stopped increasing altogether. Okay, you've just stopped. Okay. All right. Now that's sine x. Now what about x? Okay, x is also increasing. But what rate is it increasing at? It's increasing at a constant rate, right? Because you could say, I could differentiate this, which gives me gradient, and the gradient is 1. And the gradient is always 1. Forever, this line is just increasing at the same rate. Okay? So, increasing at a constant rate. Okay? Now, lastly, 10x. Also increasing, and you can probably fill in the gaps here, right? It's increasing at an increasing rate because it's approaching an asymptote, right? Sorry, it's right here. It's getting closer and closer, steeper and steeper and steeper, and it never gets there, right? So it's going to keep on increasing and increasing rate all the way up until asymptote. Okay? Bless you. Alright, therefore, what I'm going to suggest is, off the back of that idea, this inequality. Okay? Now we're used to having 2-sided inequalities. One thing's bigger than another, or less than another. But I've got 3 things here. So I want to get the relationship between all 3. Okay? So I'm going to put this down like so. Sine x, right? Just in this domain, sorry, for acute angles, okay, sine x is always going to be less than x. Does that make sense? Can you see that? And that's always going to be less than tan. So I've put these all in order, okay? I'm disregarding 0, the origin, because then this wouldn't be true. And I'm also disregarding pi on 2, because this guy doesn't exist at pi on 2, okay? All right, now, keep in mind where I'm trying to head towards. I'm trying to head towards this. This is the result I'm trying to establish, because I need it for the first principles thing, right? I can't simplify any further without it. So, how would I get from this to this? Well, to start with, I'm going to divide everything through by sine. Okay, divide everything through by sine. 1, 2, 3 parts. So this is a bit like, you know, when you've got an inequality and you say 2x is less than 4. To solve this, you divide both sides by 2. Right? And that's all happy. Okay? Now, by the way, if I had minus 2x is less than 4, and so the next line, I'm going to divide through by minus 2. Okay? What happens to the inequality? It changes directions, right? So with inequalities, like so, with inequalities you've got to be careful. It's not an equal sign that whatever you do to the right, left and right is exactly the same. The direction matters. Now tell me, as I divide through by sine x, so I'm going to get, on this side I'm just going to get 1. In the middle I'm just going to get x on sine x. Okay? And on the right hand side, tan is just shorthand for sine over cos. So when I divide through by sine, I'm going to get 1 over cos. Okay, now you tell me, how can I know that none of these inequalities have changed direction? Why haven't they, you know, how can I know? Good. I've very carefully restricted the domain here, right? And within this domain, you can see it on your graph, right? All of these are all positive. Okay, so we're just dealing with positive numbers. None of these inequalities going all in weird directions. Okay. All right, now, where did I want to go to from here? Well, I need a limit in here somewhere, right? So I'm going to apply a limit to all of these. I'm going to say, what's the limit as, I've got h over there, but these are x's, so I'm going to say as x approaches 0. Okay, so I'm going to take the limit of all 3 of these parts of the inequality. Okay? Alright, now, think through it with me. This middle part is basically where I want it. Okay, so I need to think about either side. What's the limit as x approaches 0? How is this thing behaving? It's just a constant, right? It's just 1. It's always 1. It doesn't give a rip what x is doing, so it's just 1. Okay? This limit in the middle, I'm going to leave it as it is. Now what happens on the right-hand side? As x approaches 0, what does cos approach? You can think about it from either side, from above or below. It approaches 1, because the graph for cos looks like this, right? Okay, so as I'm approaching 0, that middle part, the axis, I'm getting closer to that point there, which is 1. Okay? So therefore this thing is 1, well it's approaching 1 over 1, which is 1. Does that make sense? Now, can you see why this section is called the squeeze law? Or why mathematicians invented something called the squeeze law? There's this thing in the middle here, and I'm trying to work out what it's equal to. I've determined it's got to be bigger than 1, right? I've also determined it's going to be less than 1. Oh no, what's going on here? Okay, so really what this means is I've got this unknown thing, and I've got it constrained between 2 other things, right? And these could be other functions if you like, but just in this case it happens they're both constant. Okay? So if I'm between them, but they're both the same thing, that means that this guy here, here's my result, this limit is not greater than or equal to either of them. Sorry, greater than or lesser than either of them. It's equal to 1. Okay? So this part here, this line is called the squeeze law. The unknown value I'm after, it's literally getting squeezed between 2 other things that I do know about. Okay? Now, because this number 1, right, this is useful to me because 1 is its own reciprocal. Okay? So therefore I can say, here we go. This implies that if I take it upside down, x over sine x over x, because it's approaching 1, its reciprocal is itself. Right? And that's the limit I was after. This here. Okay? Now, by the way, this important result, right, we're using it to prove these derivatives and that kind of thing. But it's also useful as its own sort of thing when you're doing limits, okay? You remember limits was its own idea, and we were thinking about, what's the limit as x approaches 2 of x squared minus 4 on x minus 2? By the way, what is it equal to? What do?
You
Factorize the top, which will be x minus 2, x plus 2, and then that x minus 2 will cancel, so it's going to be x plus 2, so that's just 4. Okay? Now, you've looked at these kinds of things and you're familiar with that, right? So these are what we call limits of algebraic expressions. These limits here are similar, and they're the kinds of things you're going to be expected to recognize as well. Okay? Now, I said here that 3 is limits of x and sine x and tan x as well. Okay? So because x and sine x and tan x, they're all actually, if you like, they're all converging toward the same value. Okay? So I've got a lot of different ways, a lot of different combinations for how I can say this limit. Okay? I can also say, another color. I can also say the limit as x approaches 0 of, say, x over tan x. Right? I can say that's equal to, again, the limit as x approaches 0 of tan x over x, or any such combination. They're all equal to 1, okay? Because they're all converging on the same point at the same rate, okay? One more way to say it, which is that all of these things here, okay, as I consider them for really, really tiny values, so if you've got a magnifying glass out and you zoomed in on the origin, okay, we can say that sine x is approximately equal to x, which is approximately equal to tan x for small values of x. Okay, so let me just recap, because that was 2 and 3, okay? These results here that I've got down at the bottom. Number 1, which we got from this inequality. Number 2, which I got by just taking the reciprocal. 3, 4, and then this weirder way of saying it down here, 5. All of these, they're in the syllabus, and they're not to be examined, but you need to understand how they work. Okay? Sorry, I meant this is not to be examined. These can. Okay? So you might get given a limit like this, or maybe they might throw a 5 up there, which would have what effect? You just multiply this by 5. It's not that hard. So they're things you need to be aware of. So, that was number 2, and number 3, squeeze law and limits of all of these different functions.